We're going to continue describing the loss interaction in piezoelectric materials. So last time we started the description of applying an electric field to a piezoelectric material, and we get a energy diagram which has input electrical energy, then we get stored electrical energy, and then we have output or converted mechanical energy. And last time we saw the story here going on, which basically told us the expression for the constant mechanical energy, for the lost mechanical energy. So this would actually be that I form, and that was 1/2 multiplied by the area over the length times the electric field squared. 2, I forgot this 2 last time, I kind of forgot it. 2 times the tangent, so we could call this just instead of calling that single, we could just call it double prime, and that would make things a lot easier for us. Tangent phi. So we have the piezoelectric loss and the mechanical loss. Similarly, we have the other equation for the converted mechanical loss, which was or for converted mechanical energy, which is restorable. That was just going to end up being this: d squared, and that's single prime, over s single prime, which is going to be under constant electric field in this case. So these two expressions relate the energy in the piezoelectric materials. And actually this should actually be this squared SE, because then we will get a energy amount. Rather, these are percentages. So in this case, if we consider the stored mechanical energy lost, the converted mechanical energy lost and the converted mechanical energy stored, we get the following expression. So this is the sort of effective loss which is happening for stored mechanical energy. So, but we also realized that there was actually stored electrical energy, and this electrical energy is represented as following, because we have the stored electrical energy. Let's call it just a star equals 1/2, and this is going to be capacitive energy. So epsilon star AL, which is also the thickness and the length, times the electric field squared, and this epsilon star here, it's constant strain, because we're considering that the energy which is being stored as a capacitor in the stored energy, this stored energy is not causing the material to move. It's part of this energy. So because this energy is not necessarily causing the material to move, it's being stored as electrical energy, purely electrical energy, we're actually considering it under constant strain. And expanding this form a little bit, we get prime under x minus I epsilon double prime x AL squared. So you can imagine that equals you can imagine this, but this is not equal to this. See, because this is equal to epsilon double prime under constant stress. So we notice the difference. So now we're going to start to change the notation up a little bit. Okay. We're going to call this constant stress condition tangent phi with a little prime on it. Tangent phi prime. Also, just to denote, because this has to do with constant electric field, we're also going to consider it with tangent phi prime. So we'll call all of these prime. Everything here we're going to call prime now. And we're going to consider this part, which is not equal to this. It's actually different because of the different boundary conditions which are occurring. So we're going to call this tangent delta. So we see these primes coming in. And now in this case, with constant strain, it's not going to come. So we know that the energy lost in this case is the tangent phi, or tangent delta without any prime. So if we would like to continue, if you remember from the energy diagram, we had the input energy as electrical, the stored energy as electrical, plus the mechanical energy as electrical. If we consider the real part, we get the stored energy. If you consider the imaginary part, we get the lost energy. And the lost energy over the stored energy is what was the tangent factor. So, but in this case, what we're going to try to do is figure out how much energy is lost and how much energy is stored due to the application of electric field. So first we'll do the real part. And we're going to be solving for the real part of the input electrical energy. So thus we're going to use the real part of the stored electrical energy, which is just 1/2 epsilon A L little x and little x E squared, and that'll be single prime, plus 1/2 A L the electric field squared D prime squared over S prime E. So this is the stored electrical energy. All of this energy is the energy that we're storing in the material. The lost energy, all this dry nice I is going to equal, in this case it'll be 1/2 epsilon x double prime AL E squared plus 1/2 AL E squared, and it's gonna be D. We can just write it the same way, except we're gonna write this format here: tangent phi prime minus tangent phi, and this becomes easier to write it. Instead of writing all of these different factors, we can actually express this in terms of the tangents. Similarly, we don't have to write this like that. We can just write 1/2 epsilon or x epsilon ALE squared, this tangent delta, not prime because we're using the constant strain condition, tangent prime. So these are the relationships which are telling us how much energy is being stored and converted. Basically, it's telling us how much input energy there is into the material for a given electrical input. So the next thing we want to know is, so we apply an electric field, we get out stored energy and lost energy. The lost energy comes from the tangent delta. Lost energy comes from phi prime, and this, remember, this has to do with this one, and these all notations, they depend on the boundary conditions. This depends on epsilon x, and this remember, the stored energy is stored as D is stored proportional to d squared s for the mechanical side, and for the electrical side, it's stored proportional to the epsilon under constant stress. Under constant strain. So now we mentioned what was K squared. K squared equals the converted energy over the input energy. We normally don't write it in terms of the stored energy. We write it in terms of the input energy. So K squared, we can write from these are equations. So we have this total energy here, which is this is the total energy, and if we divide that now by the converted energy, which is just this portion, we'll have what we know as K squared, but it'll be a little different format depending on which variables you're using. But if we rewrite this coupling loss, this coupling term in terms of a complex parameter, we would determine these are all complex. And this is capital, and right here we have the S term. And if these are all stars, what actually was going to end up happening is we have two tangent phi prime minus tangent delta prime, and tangent phi prime, which is coming from the E. If this was SD, then this would be just phi. Just know that much. These are just notation kind of things to keep track of the interaction. This is tangent delta prime. But look up here. We were expressing everything in terms of tangent delta. So you can also express this in terms of a different way. If you just reduce this equation with all of its components, you would find that this is the relationship between, you could say, K double prime and K prime. That it would be actually this: tangent phi tangent theta minus tangent phi minus tangent delta. You could also draw your equivalent circuit that we used earlier to describe the different parameters as, we drew the top as a motional branch. So this normally has to do with the losses which are occurring in that branch would have to do with the complex value of the elastic compliance, and similarly the bottom value, their losses would have to do with the complex value of the permittivity under constant strain. And with this we apply an electric field across V equals 0 and V equals, like, say, some number, and therefore the current or the stored energy in this case would be lost and stored according to these specific values. And their interaction would be such that the lost energy would be the summation between, again, this value and this value. The lost energy. This would be the lost energy, and the stored energy would be the summation between this and this. So in this case, comparing the lost energy and the stored energy, we can derive the following equation, which I'm going to do in the next video. Thank you for watching.